Welcome back to my channel. So in this video, we are going to continue with this double integration method, and we are going to find the slope and deflection for cantilever beam which carries a uniformly distributed load. So what we are going to do, we are going to consider a cantilever beam AB of length L, and let it be loaded with a uniformly distributed load having the rate of loading small w, and it is going to act throughout the entire length. And please note the unit of the rate of loading is Newton per meter. So to further continue, what I'm going to do, we are going to continue, take a section XX, which is located at a distance of small x from our free end B. So once you take the section, we are going to find out what is the actual bending moment available at the section. And we know the bending moment is given by force into displacement. And whenever you have a UDL, the force is calculated by the rate of loading multiplied by the distance over which the UDL acts. So we get the rate of loading is minus W, and it acts for a small distance x. So this W into x will give the force, and the distance of the centroid will be half of the distance, which is x by 2. And since we are getting a clockwise moment, we will be getting a negative sign for the bending moment. So the bending moment, after finding, we are going to put in our differential equation for the deflection of the beam, which is nothing but EI d square y by dx square is equal to m. So when you substitute, you get EI d square y by dx square is equal to minus W x square by 2. So which is our first equation. So once we get that, what we will do, we will just integrate it. We will just integrate it once. So what we get, we will get EI dy by dx is equal to minus W x cube over 6 plus C1, which is the equation number 2. And C1 is the integration constant. To find that, we are going to apply our boundary condition. So let the boundary condition be at the fixed end. Normally we have the slope as 0. So what happens at fixed end, we have x is equal to L, and the slope will become 0 there. So we will substitute this boundary condition in our equation number 2. So we will get EI into 0 will be equal to minus W times, wherever x is there, we are going to put L. So we will get minus W L cube by 6 plus C1. So after substituting the boundary condition, we just simplify and we get the value of the constant C1 as W L cube over 6. So we'll substitute this constant back in our equation 2. We get the slope equation, which is EI dy by dx equal to minus W x cube by 6 plus W L cube by 6. Let this be our equation number 3, which is called the slope equation. So again, what we do, we take the slope equation and we differentiate it, we integrate it again, we will get our deflection equation. So upon integration of the equation 3, we get EI of y is equal to minus W x power 4 by 24 plus W L cube x by 6 plus we get again another constant C2. Let this be equation 4. And as you again, C2 is a integration constant. To find out, I'm going to apply the second boundary condition at the fixed end. We have deflection as 0. So we get EI deflection 0. And wherever x is there, we substitute L. And upon simplification, we get C2 as minus WL power 4 divided by 8. So this is the second constant of integration. So we substitute this, right, like this, and we will get the deflection equation, which is given by EI of y is equal to minus W x power 4 by 24 plus W L cube x by 6 minus W L power 4 by 8. And this equation is called the deflection equation. So the summary will be, for a cantilever beam which carries a UDL of W throughout the entire length, we have the slope equation as EI d square dy by dx is equal to minus W x cube over 6 plus W L cube over 6. And the deflection equation is given by EA of y is equal to minus wx power 4 by 24 plus WL cube x by 6 minus WL power 4 by 8. So thank you for watching this video. Please subscribe to learn further. Thank you.